Welcome to Almost Here, Round the Corner Future Technology podcast with Richard Jacobs. Future technologies poised to transform our lives for better or worse are the focus of this podcast. Almost here means these technologies are now here and starting to be used, or just around the corner, from Bitcoin to artificial intelligence, 3D printing, blockchain, virtual reality, and more.
Hello, this is Richard Jacobs with the Future Tech Podcast. My guest today is Risto Ugolinin. He's a CTO of a company called Sentient. He's also a professor of computer science at the University of Texas, and his current research focuses on methods and applications of neuroevolution and neural network models of natural language processing and vision. And he's the author of over 380 articles in research areas that cover these topics. So, Risto, how are you doing?
I'm doing great. Good morning.
Yeah, thanks for coming. Tell me, what is neuroevolution versus neural networks or other methods of machine learning?
Yes, neuroevolution is a particular method for training and constructing neural networks. And they've been around for quite a long time, and they have a special niche. They are distinctly different from your standard neural network training, where you collect first a data set, a training set, and you train a neural network to do something where you already know what the correct answers are, and the neural network learns a model of that data and then allows you to predict what will happen in the future with similar inputs. With neuroevolution, you don't have such training set necessarily. You have a neural network you can put into a task and measure how well it's doing, but you don't know what the correct answers are. You can only tell how well it's doing. And now evolution is a mechanism that allows you to construct that neural network, its organization, its structure, its weights, so that it performs this task that is specified only in terms of how well you perform for it. For instance, in a game playing situation, you don't know what the optimal correct moves are. You have to try things out and then see how often you win. And that kind of weak information is enough for neuroevolution to construct that neural network for you.
Well, how do you compare the results or the requirements or the speed or other factors versus neural networks or deep learning, etc.?
Right. So the end result of neuroevolution is a neural network, just like it is in deep learning and other mechanisms that use neural networks. So once you have that network, you can apply it just like any other one, and it performs just as fast. The training times, there are multiple comparisons that sometimes neuroevolution can be a lot faster, sometimes it takes longer, but that's not usually a concern because what we are trying to find is a network that performs the task, and we have plenty of time for the training. We don't have that much time when we actually have the network. It has to perform very fast. But that's a different issue, and there's no difference.
So what are some of the sweet spots for neural evolution? Where does it work best? What kind of problems?
So there's two different areas where neuroevolution has a niche or serves a unique role. The first one started about 25 years ago or so, when it was difficult to train neural networks that were recurrent, that had time-varying information and processing ability, especially those like game-playing agents, where you have to perform many actions and you only in the end you know how well you're doing. And your situations that you get to depending on what actions you take. That's typical gameplay. So it's difficult to train a neural network for such a task because there's no, like I said, optimal training data available. But with neuroevolution, we could let the network and evolutionary population figure out what kind of networks work and perform then well. And there were lots of applications of that kind and still are, where neural networks are agents in a game and they perform sequential decision tasks. They might be controlling a simulated agent avatar in a video game, in a tournament or Dota or something like that. Or they might play a board game too. And there's been many applications for instance, in Atari and other games like that. And that's where there's still a role because sometimes it is difficult to train a network to perform these sequential strategies as opposed to something where you are just reacting what's in front of you right now. Those are POMDP tasks, they are sequential decision tasks. Another role has emerged in the last few years, pretty much just last 3 years, and that is to optimize the structure or the architecture or the design of the neural network itself. And the reason is that the neural networks have gotten a lot more complicated than they were in the 90s. They have now tens, maybe hundreds of millions of parameters, but also they have a structure that consists of multiple layers of different types, dropout, max pooling, all kinds of components. And you have to come up with an architecture that puts these components together into a network that works. And it is quite challenging. It takes quite a bit of experimentation and expertise, and it's still never really clear whether you got it right. So this is the new opportunity for Neural Evolution. You evolve the architecture, the design of this large neural network system, and then you train it using regular deep learning techniques. So Neural Evolution can serve as a first step before you start your usual neural network training. And in that sense, you have your architecture optimized for the task, and you can get better performance. And there are results in the last couple of years that show that in these standard benchmark tasks for neural network, for deep learning, in vision, in language, in multitask learning, we can do better if we evolve the neural architecture as part of the learning mechanism and then train it.
So what are some examples of architecture differences that you use versus traditional models?
Well, you have to start by defining a search space first, and that's where the human expertise comes in. We know what some of the good architectures look like already for, say, vision tasks or language tasks. So we tell evolution to use these components, but then evolution is free to use them in a way that it discovers works best. And that means that you make layers out of it, you change the size of the layers, depth of filters, you add skip connections, you add depth, you add width. So in general, you are finding better architectures in the same space as what humans are trying to find. And what we've seen multiple times is that evolution often comes up with alternative paths, architectures that allow activity and information to propagate in multiple different ways at once. Whereas the human-designed architectures are often more linear. They have fewer skip connections. They have more depth and linear paths. And in that sense, we don't know yet whether it is a result of the method in that such an architecture is more robust. When you're trying to find a good architecture, they form better stepping stones in the process of finding good architectures, or whether it really is in a domain of, say, vision, it's good to have multiple alternative paths and then some kind of synergy and convergence of those. And we see some of those human designs already employ similar principles. So ResNet, for instance, multiple repetitions of modules that allow you to bypass or go through a transformation. Principles like that are discovered by evolution at a macro scale. And now there's also an interesting question. What are those principles? Can we understand them? And then can we utilize them in a more systematic way to design better hand-design architectures? So that's still research that needs to be done. But evolution gives you insights, an opportunity to discover things you don't already know.
Well, any examples of really amazing evolutionary results that changed how you work?
Yeah, there are lots of those. It's actually one of the reasons why it's so much fun to work with evolutionary optimization, evolutionary computation. And that is that there are discoveries that you don't anticipate. And if you haven't seen it, there's a fun paper called Surprising Anecdotes in Evolutionary Computation. It's in arXiv, and it's a collection of some 30 or so stories like that from the whole community of evolutionary optimization where discoveries were made that were quite surprising. And they are interesting in their creativity. Evolution does not care what you have in mind when you set up the problem. It will work within the constraints that you set up and sometimes finds very surprising solutions. So we've seen many such examples. I can, for instance, one of them is that many of them relate to robotics, like different ways of using your robotic body in order to achieve the goal. There are, for instance, robots that learn to work on their back because you tell them not to use their legs, save their legs. You have situations where evolution discovers in a game playing situation and a good move is something really, really far away because your opponents expand memory until they crash. There are also very positive solutions that humans can't really easily comprehend or come up with. So, for instance, the Shinkansen train, the locomotive, the engine, they had a very aerodynamic design, or so we thought, but it had very high boom when it got into a tunnel or out of the tunnel. So evolution was used to discover a shape for that nose cone that reduced that boom, and it was very different what humans came up with. I can go on and on. There are lots of these results, and many of them are fascinating. And in different areas. Go ahead.
When do you get this emergent behavior? Does it happen almost all the time when you use these networks, or do you have to do certain things in order to get emergent properties like this?
Yes, it is really the nature of evolutionary optimization to discover solutions. We have to give it some ammo, some opportunity to cover these surprising designs. So we have to define a search space first, such that it's large enough that there are some interesting solutions there. So we shouldn't put in too much of our own intuition. We should give it some room to explore. And the second aspect is that we should favor solutions that are novel, that are surprising and interesting. So that's one of the interesting research or scientific ideas that has come out in the last few years, a decade or so. Let's support creativity. Let's support novelty and give it a separate objective or some other way of rewarding solutions that are different from those that you already have. And that turns out to be a big boost to evolution. It can explore solutions that are not necessarily doing very well yet, but in combinations with other solutions can create something that's novel and surprising and effective. And that's where a lot of the current research is, and it has worked out beautifully. We have all of these examples where evolution discovers surprises that work. Another aspect of that question is that it happens routinely. So at Sentient, we built a website optimization system, product Ascend, Sentient Ascend, whose job is to go and optimize the design. That means the button color, the button text, the background image, layout of landing pages and other web interfaces, so that they are more effective, that users who come to the site are more likely to press the button to sign up or to buy. And it turns out, even though there's a lot of human expertise in this area, there's also a lot that can be discovered that humans have missed. And this website optimizer routinely finds better solutions. That's part of the product. We can do it over and over again in different industries and different lengths of the funnel and different product environments. There's a lot to be discovered if you let evolution to run its course and let it be creative.
Very interesting. So what's the particular focus of your research? What are you working on right now? Or is that what you covered, or is there any more specificity to it?
Well, there's a lot, of course. This is an exciting area, and there's a lot of room for new ideas. One of the opportunities is that just like for deep learning, the available computational power made a big difference. I mean, from the 90s, it increased 1 million times, and all of a sudden, the ideas that we had in the 90s now work and a lot different scale. And same is true of evolution and neuroevolution. We can come up with these scale-up experiments, and it does take some work to make sure that you actually utilize the computational power that you have available, that you utilize it correctly and you utilize it productively. So coming up with those techniques that allow us to utilize this computational power and then run these scale-up experiments, that's one area of research. We've done quite a bit of that, and other people have too. And as a result, we have these neuroevolution results that architectures that are now the state of the art in numerous benchmarks in vision, language, and multi-objective multitask optimization. But there are other interesting directions. I mentioned the novelty search. How do you encourage the search process itself to cover more space? And how do you allow it to utilize and discover and utilize stepping stones? Solutions that are not yet solutions of the whole problem, but can be used later as components of a solution. How do you find those and how to utilize those? That's an interesting area.
Well, how would you even know that you found such a thing, by the way?
That's a very good question, because you cannot really use the performance in a task as a proxy for quality. But you can probably use something similar. You can identify that here's a solution that does something well. It's not exactly your objective function. It's not the actual goal, but it's a local maximum. It performs a part of the task well, even though it fails on some other parts of the task. And therefore, its whole total fitness is low, but it's very good at some part of it. So this is exactly the research question. How do you identify them? Are they compositional? Are they something that are totally different but still local maxima or minima? That's a good question. And there's different proposals for how to do that and how to combine them. There's an interesting philosophy also that in order to be really different from what in behavior from what you already have, you must have discovered something about the domain that allows you to make such a leap to a different part of the behavior space. So if you just reward according to some metric difference, you are rewarding insight into the domain. And that's the basic idea what makes this work. And how do we utilize it to the max? That's still an open research question.
How, are there open source libraries? Are there neural network, architectures that are out there publicly, or is this more of a, it's secretive and you have to figure out your own when you're working on stuff?
Well, we certainly hope to promote research in this area and make it easy to get started. There are several implementations of neuroevolution systems, a technique called NEAT in particular, NEAT. It has been implemented many times in different languages and different domains, and there are people who have used it to solve their own problems who are not neuroevolution researchers. There's, for instance, a very fun video on YouTube by Seth Bling on Super Mario, evolving an agent for Super Mario video game. And he's a game player, not so much neural evolution research, but he used this openly available software to apply to his problem. So that's certainly possible, and it's fun to do. Now, some of the newer work, evolution of neural network architectures for deep learning, that's a little harder to get started with. There are there's some code available on the web for doing that, but also another aspect of that is that it requires a lot of computational power, and currently that's not available as easily to many people. But that's also changing. There's lots of research in evolving neural architectures without as much computational power as some of the leading research labs have.
What if you use TensorFlow, or these large companies will have some modules, like Watson will have certain modules. I mean, how limiting are they, and will those help you at all, or you really need to get your own models and customize it to what you're working on?
No, TensorFlow or PyTorch is often part of the technology. It is it gives you the language to implement those neural architectures in, but evolution is then run as an outer loop outside of that. So we run evolution to design or define the architectures, and then those are implemented and expressed in TensorFlow, and TensorFlow runs the training experiment that gives us a fitness of how good that neural network architecture is. But one thing that doesn't exist at the moment is a plugin for TensorFlow that would allow you to evolve those architectures. But there are several groups working on something similar to that, and I think that that's going to come out very soon and be available to people as an evolutionary auto ML technique. Yeah.
What's the behavior of the AI community? Are they pretty open and they sharing, or are people like hoarding models and trying to patent, specific architectures? Like, what do you see out there as the landscape?
Well, the landscape is pretty open still. There's, like I said, room for ideas, and people are publishing their ideas and then building on those architectures. So far, I haven't seen much of turf wars or anything like that. We are actually talking a lot at conferences, and we arrange meetups and brainstorm about papers and results that each other have produced. And I think that's great. That's how it should be. It's a scientific community. It includes people from industry and people from academia. Now, that might of course change if it gets harder to make progress. But at the moment, there's so much room for ideas. We can evolve certain architectures and look at what somebody else is doing, incorporate their ideas of components and structures into our method, and do better. And this has been going on for now a couple of years, and I think it will continue for a while. And it's really exciting to get into this field right now because of that. There's a lot of ideas, but there's also room for new ones. Of course, it changes so quickly that it's difficult to start from exactly where other people are. You have to catch up a little bit, but because of tools like TensorFlow and some of these tools like Neat and others, it's relatively easy to get started.
Are there any problems that appear to just still be way out of reach, no matter what you do, or there's certain kinds of problems that this is particularly suited to solving?
Well, that's a good question too. That currently the focus of artificial intelligence is on these problems that neural networks can solve well, which means a lot of data is available, and therefore we can model it. I think that in the future there's probably going to be movement towards more broad class of problems and technologies as well. So, for instance, one opportunity that I think is great in the future for applications is to combine the deep learning, the modeling, the prediction technology with this machine creativity technology that evolution is part of, and also reinforcement learning, and do something in the real world where the evaluations are very expensive, but you can use a predictive model as a surrogate. So you optimize, find good solutions with the surrogate, and before you implement it in the real world. That's a great area for the future, and I think that that's also going to keep the field going for quite a while. But also, many people, including myself, believe that there's also a role for logic, like probabilistic logic, knowledge representation, extracting knowledge and using knowledge and putting it in. And currently, that's not a very central area of research. But if we want to expand the range of applications, I believe that in the future we have to do that. We have to extract the knowledge that these machine learning systems have acquired, and we have to find ways of putting in human knowledge also, instead of having to learn it, during the lifetime of the neural network, and then making decisions that are traceable and interpretable, because we can actually understand them in terms of logic or some other knowledge representation system. So I think that's still a few years out, but that is something that is going to be important in expanding the area of AI in the future.
I've heard often that people say, like, what goes on inside a neural network or inside of these systems is a black box. What is it about what goes on that makes it a black box, and why can no one figure out what's going on?
Well, it's true that it is not as obvious as it might be in a rule-based system, and we have also at Sentient, we've developed mechanisms for evolving rule sets for this exact reason. When you evolve a rule set, you can look at the result and you can understand where the behavior is based on. And that again is an example of why not all of AI needs to be neural networks. There are maybe applications where other representations work better, and part of it is that they are immediately interpretable and understandable. But it's also not necessarily the case that you couldn't understand what a neural network is doing and what it's basing its performance on. And there may be several approaches for understanding. One of them is that you transform that deep learning neural network into something that's smaller or simpler, or in another knowledge representation regime entirely, but duplicates the behavior as much as possible. And you can perhaps get quite close to that, and now you have a system that's almost as good and also interpretable. It may also be possible to develop techniques that trace the neural network's performance in the neural network itself, and you can understand what it's basing its decision on. It may not be a rule-based explanation that covers everything it's doing, but you may be able to trace its decision and modify some of the parameters and point out what the most important inputs and features are, what it's based its decision on. So this is research that still needs to be done, but I think it's possible. It's just that the field is moving so quickly right now that it hasn't been a good idea necessarily to stop and start doing this kind of research, but we can when we get that far.
Gotcha. So what do you see as the path ahead for the next few years? Any big developments coming up, or just is it more like playing with these models and understanding them and seeing what evolves out of them literally?
Well, there's a lot, yes. So I think one big step is that in terms of neural networks and deep learning, reinforcement learning, we've come pretty far with the hand-designed complexity, and we've hit the point where it's very difficult to make progress by building larger and larger and more complex architectures. So these automated methods for designing AI systems, for designing deep learning systems, are going to be very important in the future. Some of them may be based on evolution, others in reinforcement learning, maybe based on optimization, gradient descent based, but meta learning in general, learning to construct good learning systems is going to be very important. And simply because we cannot, as humans, cannot handle that level of complexity anymore. So let's let machines do that. I think that's one important area, and there's already a lot going on in that area, and more in the future. Then, as I already mentioned, this opportunity to expand from supervised learning to discovery, machine discovery. So we are not only trying to predict what will happen in similar situations in the future, but we are creating entirely new solutions where humans don't know what the right solution is. Machines will create and discover that solution for you. Those are things like evolution and reinforcement learning that can do that, those kinds of techniques. And then putting these together into surrogate modeling, applying to self-driving cars, to health care treatment recommendations, to automated agriculture. There's a role for modeling what will happen if you give a certain kind of recipe, implement a certain kind of recipe for growth or for treatment. And then there's a role for finding that recipe. Humans don't necessarily know that, but what a good recipe is, but machines can. So you put these two together, you have a model that allows you to test these recipes while you're searching for a good recipe. And then when you find a good recipe, that's implemented. That surrogate optimization, I think, is going to be a big opportunity to expand artificial intelligence in the future as well. And then at the very end of it, and the furthest that I can see, interpretability, understanding what is being learned and expressing it in some kind of a logical, probabilistic logic, perhaps. That's going to be also important, and the research is starting already, and in the next 10 years or so, we'll see more of that too.
Okay, well, very good. Is there any, I guess I call it like neural network artwork? Are there any like graphical representations of various networks and how they're connected out there?
Yes, there's certainly a lot. You're referring to Neuroevolution produced architectures, I suppose. Yeah, I mean, part of it is to visualize.
And traditional ones, yeah.
Yes, there's certainly part of the success of neural networks is to come up with better architectures that perform the task. So there are lots of illustrations of what people have come up with, and also what the discovery systems have come up with. So they tend to be pretty complex and have a lot of detail in them, but it's certainly interesting to look at them. And it allows you to appreciate the complexity when you see those graphical forms.
Any references where people can find them, or do you have any links? Or
I can supply those, but not on top of my head. I would have to go and find them, and then maybe email.
Sure. No problem. All right, well, that's great. I appreciate you taking the time to do the podcast, and thank you so much.
Well, thank you, Richard. It was a pleasure. Anytime.
You have been listening to Almost Here, Around the Corner Future Technology podcast with Richard Jacobs. Subscribe to this podcast, post a review to discover more future technologies that are poised to transform our lives for better or worse, such as Bitcoin, artificial intelligence, 3D printing, blockchain, virtual reality, and more.